So basically, and that's important, they reduce the sun to a black hole. Okay? That is, the radius of the sun becomes 18 kilometers, or approximately that, for a black hole. And then they write the equation, and they get the correct orbit for the Earth around the sun. But then they don't turn around and say the sun is a black hole. Right? So, however, that's the equation they use. You can imagine that maybe, just maybe, there's a layer of the sun, okay, that's the plasma we see all around the sun, and that inside it's collapsed into a black hole. And we would never know. Although we would know if we thought about it, because the equation we'd use to solve the orbits would be a black hole equation. You guys are following me? So I use that, but in this case, I know what the radius of the proton is, so I'm not trying to figure out the radius. I'm trying to figure out, in such a radius, how much mass do I need for it to be a black hole? So I had to change it around. This is the way it is, right, over there. So mass is unknown. But I wanted to know mass. So I had to flip the things around, and I got the result. I don't have time to give you the details. I'm sure you're all interested in them. The result is 10 to the 14 grams proton. And that makes the proton a black hole. And if you actually figure out how much of the vacuum energy you've used from the 10 to the 55, you've used 10 to the minus 39% of what's there. So you've used teeny weeny little bitty little amount of the amount of energy of the vacuum to produce all the protons in the universe. Just a little teeny weeny billionth of a percent to produce all of the matter in the universe. So imagine if we tap that resource, which we can. Which we are, as you are alive, tapping it right now. Now, if you say this to a physicist, you're going to encounter a large objection. An objection of about 38 orders of magnitude. The physicist is going to say, you got a proton of 10 to 14 grams. The measured mass of the proton is 10 to the minus 24. You're off by some 38 orders of magnitude, dude. So how do we resolve that? I mean, when I came across that, I knew when I got 10 to 14, okay, it's not the standard mass of the proton. How do we resolve that? It took me a while, and then I realized the key is the strong force, dear one. What is the strong force? When we found protons, we found that they were positively charged and that they would repel, just like two magnets of the same charge would tend to repel. And if they're strongly magnetized, you can't get them close together. So imagine protons squished in a little nucleon atom with the same charge. How can that be possible? When we found that, we were like, oh. And since we didn't have black holes, Einstein had just finished his equation that predicted singularity, but everybody thought that's impossible, right? They said, okay, they must, and so gravity could not be strong enough. We didn't have singularity black holes. So they said, oh, there must be a force we don't know about. We'll call it the strong force. And we'll make it exactly the amount of force necessary to force the proton together into the nuclei. How convenient. But nowhere was it given as a mechanism of this force. That is, where did this force come from? Where did the energy come from to produce that force? It was just thrown in there as a fudge factor to squish the atom nuclei into existence. Later on, and they calculated it had to be very, very strong. Later on, they realized that the proton has little bits inside it that are even smaller, called quarks. And now the quarks are charged, so they now needed an even stronger force to squish the quarks into the middle. Now that's embarrassing. You can't call it the strong force. So they got artistic. They called it the color force. And so the color force was deemed to be infinitely strong at the quarks level. Like that, you know, if they found anything smaller, they had infinitely strong force to deal with it. And that this strong, infinitely strong color force was mediating force to the proton level using gluon particles. Gluon. So that's when I asked, who's making the glue? Because nowhere in this whole scheme did they say where the energy come from to produce an infinitely strong force. But if you have an infinitely strong force confining to the center of a particle, what do you have? A black hole. Right? So, I said, okay, since latex QCD doesn't give, you know, gives computational results and no analytical results, which is the way they deal with the scheme of the strong force. If you ask a physicist, how strong is the strong force, they'll say, we can give you a ratio. If gravity is 1, then the strong force is, guess what, 38 to 39 times stronger. Exactly how much my proton is off by. Right? So I said, well, you know, in my case, I'm accounting for the energy necessary to produce the gravitational force that confines the atom. You guys don't. So obviously, you guys are off by 38 orders of magnitude. It's not me, it's you. However, I knew that wasn't gonna, you know, go far. So I figured I'd give them a scaling law to see if I'm right or they're right. So I made a scale between the radius of an object and its mass, the radius and its mass. And I put the universe, and I put everything I could throw in there, like local clusters, galactic centers, galaxies, whole galaxies, galactic cores, pulsars, the whole thing, the sun. I mean, I threw the Earth in there. I mean, the whole thing, to get like as accurate of a trend as possible. And then I put in the Schwarzschild proton mass. And it fell very nicely along that line with all the other objects. And then I put the standard proton mass. And that was the only data point off the chart, literally. And so that confirmed, in some ways, that obviously the Schwarzschild proton is realistic relative to all the rest of the universe, and that's straight data. It's not out of equations. So, but when I did this and when I published it, I knew there was going to be some controversy about it. Why? Because the universe here is the universal mass is calculated by adding all the standard protons' mass. So that mass is the result of all the standard protons' mass added together. If that was the correct mass, then the universal mass would be off the chart, and all the data points on it would be off the trend. You all following this? So that was a problem. And, you know, I knew that was a problem. When I published the Schwarzschild proton paper, I didn't claim that it was complete. It was just an impetus in one direction. What was really wonderful, however, is that when I looked at the black hole protons, if I orbit them around each other, I got many of the data you get from the standard model. Like I got the correct gamma ray emission, I got the correct interaction time, I got the correct magnetic moment, I got all this stuff correct, so I knew it was correct, but I had to solve this. How is it that it can express two different masses? And this is what I just solved. This is what I just published. And the result is like way beyond my greatest expectations. So I'm going to show you what I did. The first thing that happened, it was middle of last year. I said, okay, well, we have a little proton that has 10 to the 55th grams in it, the mass of the universe in it. And you know, it may be, if this is true, if it's the true holographic representation of all the other protons in the universe, this may be the first time we get an exact number for the mass of the universe. And I knew there was this big problem in physics. It's a problem that's part of the vacuum catastrophe. That's 102 orders of magnitude problem. 122 orders of magnitude problem. And that's because, remember I was saying that that the universe has this dark energy in it that's inflating the universe. The vacuum has this energy in it at the cosmological level. When the physicists calculated the density of that energy at the cosmological level, they found that it was 10 to the minus 29 grams per centimeter cubed. All right? So it's a really, really teeny amount of energy per 30 minutes. Okay. And at the quantum level, it's 10 to the 93. So it's a huge difference. If the vacuum has 10 to the 93 grams per centimeter cube at the quantum level, how is it that we're measuring 10 to the minus 29 grams at the cosmological level? And there's 122 orders of magnitude different. That's huge. That is currently the largest problem in physics ever encountered. It's commonly referred as the worst prediction physics